Hi everyone, I'm Thong Nguyen, a research fellow from Future Drought Hub at USQ. I'm going to talk about geographic distribution and diversity as a feasible adaptation strategy to manage systemic risks in farming systems. As we know, climate variability strongly influences agricultural profitability. In particular, extreme weather conditions such as droughts, floods, and storms can lead to a partial or complete loss of crops. For example, gross farm production in Australia has dropped by 27% on average during drought events over the past 50 years, and the damage bill from the recent flooding in Queensland and New South Wales is expected to top $2 billion.
This means that where they can, today primary producers need effective risk transfer solution and adaptation strategy in farming to reduce the losses. However, the spread of extreme events over location in terms known as systemic risk is also a significant challenge for implementing risk transfer solution and adaptation strategy. Many risk transfer solutions and practices have been adapted, such as insurance contracts, crop rotation, and so on. But here I'm going to talk about my applied research into the geographical diversification strategy. That is, we diversify farming system across different geographic areas to reduce the impact of the systemic risk and the changes in other type of factors. More specifically, because the impact of climate varies from location to locations, we propose a framework based on a modern portfolio theory and statistical technique for spatially diversifying farming systems for two study cases: wheat crop and grazing. The ultimate objective is to optimize the trade-off between profit and loss. We know it isn't possible for everyone, but it can be an option. For the first case with wheat crops, we address the problem that suppose we are growing wheat at three different locations. The question then is what the percentage of the total hectare should be allocated to each location to achieve our expected profit and risk target reduction. To demonstrate the problem, we selected three locations located in Victoria, South Australia, and Western Australia with the historical data from the Department of Agriculture and Water Resources as the case study. From the figure, we can see that the marginal return in South Australia appears to be the most stable, except for 2007 and 8. The extreme losses occurring in all zones for the periods 2006 and 7 may be associated with one of the most severe drought conditions on record, caused by the El Nino events across most of Australia. However, we can see that the marginal return at each zone generally move in an opposite direction to that in other zones. We can see that during the El Nino years in 2006 and 7, while the marginal return at the South Australia and the Western Australian farms dropped sharply, that at fish farm increased considerably. Or we can see that the marginal return at wheat and South Australia farms fluctuate during the 5 consecutive El Nino years from 1991 to 1995. However, that of the Western farm remains stable or increased. It may not seem like it, but the unpredictable nature of the marginal returns at these study zones actually suggests that the geographical diversification can be considered a feasible risk management strategy to reduce the losses. From the figure, we can see that the result gives the options that the optimal share allocated to each growing zone varies depending on the different expected marginal returns and risk levels. For the second case with grazing, we address a similar problem. However, we involve the ancestral information into the model so that we can compare the diversification option with and without the climate information. For this study, we selected 4 locations in Queensland, the Northern Territory, and Western Australia. From the figure, for example, in the neutral phase, if we allocate 20% of production to the Kimberley and 80% to the Barkley tablelands, that gives us an expected business profit of $2.3 per hectare and risk of 1.3 per hectare. A risk taker might allocate production to the Charlottesville and low-risk areas in a La Nina years to reach the highest expected business profit of $4.1 per hectare, but with the potential high risk of $8.5 per hectare, with the average of on extreme loss lower in the worst 5% of cases. However, in the same La Nina condition, a risk-adverse producer with the means could instead ship about 23% of their production to the Kimberley and 20% up to the Barkley tablelands for a risk reduction of 25% and a risk reduction in expected business profits of 41%. In general, the optimized portfolio models provide a better range of risk reduction and profit increasing options relative to when ancestral information is used compared to when it is not. The research framework applied to other parts of the world and could provide value-based information for agricultural risk reduction and insurance solutions. Again, we recognize having property across a range of regions may not be possible for all producers, but this model can be useful to those for whom this is an option. Thank you very much for listening.